Okay, let's continue. So, when we're talking about ionic solutes in water, so that would be things that are ionic compounds, we need to talk about the hydration energy and the lattice energy. And these are going to be the opposing forces, the one that's going to keep the crystal together and the one that's going to pull it apart. So, the ion dipole force is one that we will be talking about as well, and I will define it later on. But it is basically the interaction between an ion and, in this case, a water molecule. Hydration is the energy that it takes. Sorry, hydration is the act of ions interacting with water molecules, and we can see that here. So, in this lithium fluoride, you have a water molecule with the partial negative side being attracted to the partial positive side, or the not the partial positive, sorry, the entire um, positive ion, right? Negative attracts positive, and we have the positive side of the water molecule attracting with the negative fluorine ion. And so this is hydration in action, basically. This is the hydration of a lithium fluoride crystal, and this kind of interaction where you have this dipole right here, right? We have electron density going toward the oxygen, and some sort of ion that's called an ion dipole interaction, right there. So an ion dipole force is another way, but it's another type of intermolecular force. And so if we were to zoom in on a crystal of lithium fluoride and see what was actually happening, you would be able to see that the lithium fluoride crystal is being surrounded by these water molecules from every angle, and it's being surrounded, and it is also interacting with the partial negative and partial positives. And so, if the force between one of the lithium and fluorine lithium plus and fluorine minus ions, like right here, this little interaction right there is weak enough, then you can get the extraction of those ions into solution, and you have interaction between the water molecules to be able to pull that ion away from the rest of them. And so that would be the actual act of this crystal dissolving in the solvent, which is water. And so the interaction that we were talking about between lithium and fluorine is the lattice energy, which we've covered a little bit of, but basically it is the amount of energy it takes to break apart the crystal lattice. The lattice energy holds the ions together. So, like you have this lithium bound to fluorine, it would be like this bond right here. It's that interaction that they have in the crystal lattice. And the energy of hydration is the amount of energy that it would take for the amount of energy that is associated with an interaction between the ions. I drew that backwards, but that's okay. An interaction between the ions and the water. So we have oxygen. Oh, I didn't draw that backwards. That's okay. Interacting here. And so if the, as I said before, if the energy of hydration is more massive than the energy, the lattice energy, the amount of energy holding those together, then you will have something dissolve. Okay, so a stronger ion dipole force, meaning the force between the dipole, let's say water, a stronger ion dipole force. So this one is stronger. Um, means that you will have a favored dissolving, especially if it is well, yeah, okay, so it'll have a favored um It'll favor dissolving. If you have instead a stronger force between the two ions than the um, ion dipole force, an ionic uh, lattice energy, then what's happening to me? Okay, so a stronger ion dipole force between the ion and the solvent. So if we have a solvent here, like H2O, and that is attracted to this ion, and this is stronger than the interaction between these two ions, means that you will have something dissolving. If instead your lattice energy, that would be the force between the ions, is stronger, then that will not favor dissolving. And so, one other thing that should be mentioned here is that lattice energy, we kind of went over this briefly, but lattice energy is able to be calculated using this equation where you have KQ1, Q2, and you divide that. I believe it's R squared. I don't quite remember. It doesn't matter though, um, because the R is on the bottom. That's really what matters, is that the radius is on the bottom. And so this is going to be the radius between the atoms. Really, this is the distance between the atoms in a crystal structure. And the Q's are going to be the charges. K is just a constant. It's called a spring constant. It just sticks around there for that. But the higher the charge you have and the smaller the distance between the atoms you have, the stronger your lattice energy will be. And so, since um, smaller atoms are definitely going to have a smaller distance between the atoms, your lattice energy is going to be higher. So, it's going to be a bit more difficult for smaller atoms to be able to break apart. It's going to be more difficult for the energy of hydration to break apart that atom. That being said, smaller atoms, like let's say that this is lithium with a plus charge, lithium plus is a very, very small atom, which means that it is a very small, it has a very high charge density, right? There's a positive charge on a lithium atom in a very small space, in a very small amount of volume. So you have a high charge density for a lithium atom, and that is going to increase the amount of energy of hydration that you have. It's like it's more polar almost. This is going the hydrogen is going to be more attracted to that center because it's small. So it really is a balance between hydration energy and lattice energy when you're talking about size. And so we'll go so smaller. So to summarize that, smaller ions mean higher lattice energy, and they also mean higher energy of hydration. So let's keep that in mind for this next part. Go ahead and try this out. I will reveal the answer afterward. Okay, so we have a hypothetical compound of A, B2, which is really soluble in water, and a hypothetical compound of Cb2, which is only slightly soluble in water. These both have the same lattice energies, so that's important to note. So if they have the same lattice energies, then what is it that is going to make Ab2 more soluble? Well, that comes down to the size of the atom. So the A2 plus ion must be smaller, and so it has a greater energy of hydration. Because it is smaller, it's going to be able to have a greater energy, and the lattice energies are the same, um, so the energy of hydration is going to win. So generally, when we're thinking about solubility, solubility is going to depend on temperature. So in general, as you go up in temperature to, let's say, 90 degrees or so, you end up getting more and more you end up getting more and more and more soluble. Now, this isn't always the case, as you can see for cerium selenate right here, this one. That goes down. It depends on a couple of factors, but in this is a rare instance in which the energy is going to, or sorry, the solubility is going to decrease with increase of temperature. But it does exist. Generally, as you go up in temperature, your solubility is going to go up greatly. And so we'll keep that in mind as well. But let's talk about why this might happen. So, when we're talking about solubility increasing with an increasing temperature, um, this is true because if you have a crystal, um, and you increase the temperature of it, it's going to get closer to melting. When it melts, then you have gaps in the crystal, you have ions leaving and whatnot. And you also, let's say that we're putting this in water, the more energy you put into the water, the more it's going to move around, maybe bump into these crystals more, and it's going to rip those apart. And so you will be able to you'll be able to solubilize things. And if we go back just briefly, we talked about supersaturated solutions and how to get them. And so when you take a uh let's say that you had some water and you are then going to heat that water up to near boiling and add as much salt as you can. Remember, solubility is going to increase at the higher temperature, so you can add more salt than you normally would to that water. Then, as you let it cool down, that's when the crystals start to form, because they will be super saturated. So this is one of the ways that supersaturation can happen. You can heat up all of your solution to a point where the amount of allowed material to be dissolved into that solution is higher, and then slowly cooling it, you will then have a supersaturated solution. If you disturb that, you will probably cause precipitation or crystallization in this case. And so that's the trend you see there. As you increase the temperature, the solubility also increases. But let's talk about the differences in the heat of solution of things so that the to describe how solubility can decrease in some cases. So if you have something that when you dissolve it is going to absorb heat, um the temperature of the solution is going to decrease as the solubility dissolves, and the solubility is then going to increase when you increase the temperature. But if you have something that releases heat when you put it into water, then you will have something that decreases as temperature increases. So this is the reason why um, you can have some things go down in solubility as you raise the temperature. It's because you're pushing the reverse reaction, which I believe we are about to talk about very shortly. And so We can talk about these. So instant hot compresses, they use an exothermic solution process. So that means that it's going to give off heat when you activate it, and so heating it up would decrease the solubility. Endothermic solutions like cold packs are going to take in heat, and so if you heat them up, that will increase solubility. And so, in general, um, we when we're talking about liquids, pressure is not really something that we can consider. Liquids are considered to be incompressible, which means that they don't really do much. However, if you have um, some kind of gas above a solution and you increase the pressure, you push that piston down, you will increase the solubility of that gas within that liquid. You're literally forcing those um, those gas particles into the solution. So you're going to increase their solubility. And so if you've ever seen a soda stream, this is exactly what's happening. You are in a soda stream, you're taking regular water and you are taking CO2 gas and putting it, basically subjecting that water to a very high pressure of CO2 gas. That forces the CO2 into the water, and that's how you get a carbonated soda out the other. Okay, so let's talk about Le Chatelier's principle, which is a topic that we can go quite in depth to, but we're only going to touch on it briefly here. Now, what's important here is that we talk about what it means and what equilibrium is. So, when a system is in equilibrium, that means that the rate of the reactants and products forming one another is the same. So, let's say that we have A plus B going to um, A, B. Now you might notice that I drew a kind of a special arrow here. This is a reversibility arrow. So that means that this reaction is going back and forth between the products and the reactants. We can call the product or the forward reaction R1 and the backward reaction R2. Now, equilibrium exists when we're talking about the rate of the reaction. So, R for rate, when the rate of the reactants becoming products is equal to the rate of the products becoming reactants, then we have equilibrium. And so, what Le Chatelier's principle says is that if you change the temperature, pressure, or concentration um, of the reactants or products, then you will shift the reaction one way or another. And so, what that means is that let's say that we have uh, a 1 molar solution of a 1 molar solution of B, um, and we end up getting some kind of molarity on the other side. If we increase the concentration of A or B, we'll start with just A, we'll make it 2 molar, that will shift the entire thing over to this side, and you will make more of your products. So you increase the reaction, you will shift it all the way to the right-hand side, you will get more of your products being made. If you decrease the amount of products being made, you will also get more of your products being made because there are no, or if you decrease the amount of products that you have, there will be more products being made because you are now removing the product and it is no longer at equilibrium. And so that's basically all it's saying, but really what we have to say is that uh what Le Chatelier's principle is saying is that reactions, chemical reactions, strive to reach equilibrium, and if you disturb that equilibrium, then they will try to reestablish it. For example, you take out some of the reactant A, then you will shift the reaction in the reverse direction so that you can make more of reactant A so that the rates will be the same again. So equilibrium, and we'll explore that a little bit more. But first, let's talk about some colligative properties. Um, that last reaction will come up later, but the colligative properties are more important for now. So colligative properties of solutions, these are properties that depend on the amount of solute molecules or ions present in your solution. But not the chemical identity. It does not matter what kind of ion you have, it or molecule you have, it just matters that you have the number that you have. And so this is where I'm going to talk for a while. I will show you some equations and stuff and how to calculate the different properties. What I'm looking for for you to understand is not how to use these equations. I would just like you to understand what these colligative properties are and what they mean, how they're used, etc. And yeah, and so don't worry too much about the math portion for this. So let's talk about what the different variables we can use for measuring colligative properties are first. We know what molarity is. We've talked about mass percentage of things before, so mass percentage of a solute is not going to be too much different. Molality and mole fraction may be two new things that we have to discover. So first, molarity, just as a refresher, molarity is a large M, a big M, an uppercase M, and it is measured by the number of moles of solute divided by the number of liters of solution. Um, it, it's the concentration of a reaction. Mass percentage of the solute is the same as mass percentage is calculated any other way. We just take the mass percentage of a solute and divide it by the mass of the solution to get, and multiply it by 100% to get some kind of percentage. And we've covered this, so I'm going to continue to some stuff that we have not talked about yet. So, molality. And I just want to apologize right off the bat. Molarity and molality sound very similar, but they are not the same thing. Molality is measured as the moles of a solute divided by the kilograms of a solvent. And so this is a little bit new to us, but it's measured in a very similar way to how molarity is. It just uses different units. So this is going to be moles over kg, mkg. Okay, and so if we want to determine the molality of a solution containing 5.67 grams of glucose dissolved in 25.2 grams of water, we're going to use this molality equation to do this. And so go ahead and give this a shot. I'll write this down. Little m equals moles of solute divided by kilograms of solution, I believe? Solvent. Okay, go ahead and try it. I'll be right here. Okay, the first thing we need to do is find the moles of solute, which is 180.2 grams per mole. And so we'll make a little train track and find the number of moles of solute, which is going to be 5.67 grams. We'll divide that by 180.2 grams for every 1 mole of glucose, which gives us 0.0315 moles of glucose. The next thing we need to do is we need to find out how many kilograms of our solvent we have. Our solvent is water. So our kilograms of solvent is going to be 25.2 grams. We will um, convert that to kilograms. There are 1,000 grams and 1 kilogram, and we end up getting 0.0252 kilograms of water. So, to find the molality, all we have to do is take the moles and divide it by kilograms. That would be 0.0315. Divide that by 0.0252. And let's go over here. So, we have our answer right here, which is 1.25 molal. That's how you say that. Glucose solution. Now, let's just go through that one more time. We have 5.67. Divide that by 180. 5.67, we'll divide it by 180 to convert it to moles, and we get 0.035. Then we need to convert grams to kilograms, and that's it. We just divide one by the other. It gives you molality. And so molality will come up again later. The other thing is mole fraction. So mole fraction is very similar to percent mass or percentages. It's just we don't multiply it by 100% and we use moles instead. So moles of solute divided by total moles of solution. So for example, if we have NaCl and H2O, then we would put NaCl on top, the moles of NaCl, and then the moles of NaCl plus the moles of H2O on bottom to find what the mole fraction would be of NaCl. And so let's go ahead and try this one out. We already have these values from before, but well, not quite. Go ahead and try this on your own. I will write down the mole fraction equation right here. We have moles of solute divided by moles of solution. Try it out. Okay, so from before, I know that 5.67 grams of glucose is going to be 0.315, I believe. Yes, 0.315 through 0.0315 moles of glucose. And we'll divide that by the moles of water. So that's going to be 25.2 grams of water. The molar mass of water is 18.01 grams for every 1 mole. And that gives us a value of 1.40 moles equals 1.40 moles. Now we're not done yet because we need to find what what we're going to put down here. The moles of solution is not just the moles of water. It is the moles of water added to the moles of the solute. So that's going to be 1.40 plus 0.0315. And we'll add those together, we get 1.4315. And we'll put that down here, 1.4315 moles of solution. And we divide those by each other, we end up getting the mole fraction being 0.97. All right, let's keep going. So we can convert between concentration, such as molarity, to molality, or mass or moles, or whatever we need to. And so let's try this. We want to find the molality. And so just as a reminder, molality, little m, that is going to be moles solute divided by kilograms of solvent. A solution is 0.15 mole fraction glucose and 0.85 mole fraction water. And so this is going to take a little bit more work, but go ahead and try it out, and then we will continue. Okay, so what we can do here is we can assume, well, we don't even need to assume actually. So um, the mole fraction is X, which is going to be the moles of solute, or sorry, the moles of solution divided by the moles of solute. So first, let's find what the moles of solution are. So we have 0.85 and 0.15. We add those together, that's going to be 1.000 moles. So that's what we have right there as our moles of solution. Our moles of solute is going to be our solute. So we already actually know what to put up here. Our moles of solute is going to be 0.150 moles. Now, for the moles, if the mole fraction of water is 0.85 and there's only one mole of the solution, then we can just stick with 0.885 0 moles and figure out how many kilograms that is, because we need that in kilograms. So 0.850 moles, we have 1 8, nope, we have 1 mole of water is 18.01 grams, and we need this in kilograms. So that's going to be 1,000 kilograms in 1,000 grams in 1 kilogram. Okay. Once we do this math, we end up with this. So we took the number of moles, we converted it to the number of grams, which then was converted to the number of kilograms. Then you took the number of moles of the solute, divided it by the number of kilograms, you get nearly 10, which is 9.80 molal. I don't know how you say it. It doesn't really matter. We're only going to be using this a little bit, but it is important to know what molality is, especially for Chem 102. So there you go. If we want to convert molarity to molality, then we need the density of the solution, because molarity, remember, is moles divided by liters, and we're trying to go to moles divided by kilograms. And so if we know what the density is, which is in grams per milliliter usually, then we can convert between liters and kilograms. And so we see that here. An aqueous solution is 0.273 molal KCl. The we want to find what the molar concentration is, and we know what the density of the solution is in grams per liter. Now, if we determine the mass of KCl, um, we want to first start with the molality, um, which is 0.273 moles of KCl. KCl divided by 1 kilogram of solution. Um, we will then be able to take these moles, convert them to grams, and then we will have the number of grams of KCl that is. Once we have the number of grams of KCl, um, we will add that mass of KCl to the mass of the water, and we end up getting 1.020 times 10 to the third grams. That is going to be our mass of the solution. And so we can convert that using the density to number of liters of solution, and we can find the molarity by taking the number of moles and dividing it by the number of liters to get 0.271. Okay, try this one on your own, and then we'll walk through it. Okay, let's use this as a different example. We have an aqueous solution that is 0.907 molar lead nitrate. We want to determine the molality of lead to nitrate in this solution. And we have the density of the solution in grams per milliliter. And so the first thing that we're going to do is we're going to assume we have 1 liter. And the reason for that is because 0.907 this can be broken down into moles for every 1 liter. And since this is a measurement of concentration, and so is molality a measurement of concentration, we can use both of these terms um, to convert one another, and we can make assumptions. So the first thing we'll do is we will convert to the number of milliliters that we have so that we can find the number of grams of the solution that we have. So we'll take the density of the solution, multiply it by the number of the volume of the solution, and we'll end up getting 1.252 times 10 to the third grams of the solution. Okay, so we take the number of moles that we have, and then we need to find the number of grams of the lead nitrate that we have. And because molality is moles of solute divided by or kilograms of solvent, we need to know how many kilograms of just the solvent we have. And so we have the if we have the mass of the solution, which we just previously calculated here, right? The mass of the solution, and we have the mass of lead nitrate, then we can subtract one from the other to get just the moles or the mass of the solvent by itself. We end up with 0.952 kilograms, and then we can take the moles of the solute and divide it by the kilograms of the solvent. We will end up getting 0.953 mole PbNO32. Okay, so now that we have covered molality and X, which is the mole fraction, we can go on to the colligative properties. So colligative properties are properties that are dependent on the concentration of molecules or ions. And so colligative properties of a substance are properties that are going to change based on how much of a solute you have. Specifically, that is going to be the vapor pressure and the boiling point, the freezing point, and osmotic pressure, which I'll get into once we get there. Vapor pressure, boiling point, and freezing point, though, we do know. We have covered already. So vapor pressure is going to depress, which means that if you have something that gives off vapor, the amount of vapor it gives off is going to go down depending on how much of the solute you have. If you have more solute, you will elevate the boiling point of your substance. And if you have more solute, you will lower the freezing point. You will also change the osmotic pressure. We will get into that though. So let's start with vapor point depression. So vapor point depression, or sorry, vapor pressure depression We have talked about vapor pressure already. It's the amount of pressure of a gas coming off of your liquid. It's equal to the vapor pressure of a pure solvent minus the vapor pressure of the solution. So we have to find out what the vapor pressure of the solution is. The partial pressure of a solvent, Pa, um, is going over a solution equals the vapor pressure of the pure solvent times the mole fraction. So if we know what the mole fraction is of a solution, and we know what the solvent's pressure is without anything else in it, we multiply those together and we will get the vapor pressure, the Pa of the solution. The mole fraction of the solution is always going to be less than 1, so you're going to get something that is going to be less than what you start with, right? So if this is a number that is less than 1, then we multiply it by the standard pressure of your solvent, then we are going to get a number that is going to be less than the standard pressure of your solvent. It's going to be less. Okay. And so, moving on from there, we can talk about boiling point elevation. I'm not going to get too into what each of these things are. I'm just going to show you general trends. So, boiling point elevation is another colligative property of a solution. And what this means is that the boiling point of something that you have is going to rise. So, if we think back to once you make a solution. So, if we think back to the pot of water that we were using to make pasta. This is a common misconception of exactly what you should do when you are boiling water um to make pasta. So you want to salt the water, right? So that your noodles will be tastier. However, when you salt the water is important. So let's say that we're trying to heat this water up and we add in the salt first. Well, adding in the salt first is going to make there be ion dipole interactions. So before you had water by itself, and it already had some pretty strong interactions, right? You have these hydrogen bonds being formed. However, if you add in a some kind of salt, you now have more interactions. So not only is this going to make your surface tension, all of the properties that come along with adding in ions to a solution increase, you're also going to raise the boiling point. And that's because now you have interactions between sodium and water that are going to hold those molecules down. So it was at one point 100 degrees Celsius that you could boil water at. But adding these in might make it 105 degrees Celsius or something like that. So it's going to take longer for your water to get all the way up to 105 degrees than it would be for 100. So, just as a tip, if you're ever going to boil water for making pasta and you want to add salt in it, add the salt in right before once it's already boiling, right before you add in the actual pasta. That way, you can boil the water when it's more pure, and then you add in the salt, and it will already be boiling. And you actually, next time you do this, you'll see that the water will probably stop boiling around the water, and that's because, or around the salt, and that's because right around the salt, the boiling point is increasing. And so we can measure this by the boiling point of the solution minus the boiling point of the pure solvent, right? So that's going to be it's like T final minus T initial, but it's also there's going to be this KB value, which is a constant that is intrinsic to each different type of solvent And then you also have the concentration of your salt present in there. Similarly, you will get freezing point depression with ions. So, if you've ever lived anywhere in a cold state where the roads freeze over with ice, oftentimes they will salt the roads. And this is the reason why. It's because freezing point depression is going to occur. So, if you have an ice cube and you add some salt to it, you will lower the temperature at which ice freezes. You will lower the temperature at which water freezes, and so it will be less likely to freeze at whatever temperature it is outside. If it's cold enough, it'll still freeze, but you will be changing the temperature. And that is not because you are adding more interactions. You definitely are adding more interactions, but you're also if you are also disrupting the crystal lattice. So if you've ever seen a snowflake before, you know that water likes to make nice hexagonal shapes. Water likes to make nice hexagonal shapes. And if you add in something else right here, let's say, it can't quite make that bond to from one molecule of water to another, and so it's going to disrupt the way that it is going to be able to form ice, and it's going to lower the temperature at which ice can be made. And we can use the same equation here. It's very similar to the boiling point one. It's just about freezing point. And so we have this table of constants here. So KB, the boiling point constant, and KF, the freezing point depression constants. It's for different types of molecules over here. It's not super important, other than that this is a table that you would get some. Okay, now onto osmosis. So osmosis, if you guys have ever seen Osmosis Jones, has nothing to do with that guy. Osmosis is when you have a semi-permeable membrane. So something like a paper towel is a semi-permeable membrane. Semi just meaning kind of, and permeable meaning that things can go through it. So things can kind of go through a semi-permeable membrane. Um, Solvent can flow through it, and the concentrations will equalize out. And this is going back to Le Chatelier's principle. Semi-permeable membranes allow solvent molecules to pass through, but not solute molecules. So this is an example of that. You have this semi-permeable membrane right here, in which you have molecules that are too big to fit through the holes. Water, however, if this is water, these are water molecules, can go straight through because they're small enough to do it. Um, it's a filter in other words, but there's equilibrium that can be reached. And so osmotic pressure uses this symbol pi as a measurement, but it also will at a certain point the amount of solution in this tube is going to rise because the semi-permeable membrane is going to suck in water so that the glucose molecules will have a full saturation. And so your osmotic pressure is the amount of pressure it would take to get all the way up there to that top point. It can be measured according to this equation where you have molarity, R as another constant, and T as the temperature. And you can see the semi-permeable membranes are throughout your body. And so you can see the flows of water in and out of individual cells, um, and that are undergoing osmosis. Uh, So maybe it has a little bit to do with Osmosis Jones. So just to reiterate, these are the equations that we would be using. The I right here, which shows up in each of these, this is the number of ions per formula unit. But Again, I'm not going to be testing you on these things. You will likely go over this again in 102. Okay, so for the final section of this lecture, we're going to talk about different types of mixtures that you might encounter. So the first one that we're going to talk about is called a colloid. A colloid is a dispersion of particles that are in a different substance. A really famous example, I mean, fog is a good example of this, right? You have little water droplets dispersed in air, but another really famous example that just recently won a Nobel Prize, I believe it was last year, is the nanodot. So, nanodots are tiny little crystals, basically, where you have ordered um, substances. So, oftentimes they are cadmium and selenium or sulfur, and they are surrounded by organic molecules that will keep it in a solution without actually dissolving these. So the crystals stay together, but they are evenly dispersed. And carbon or nanodots have really cool properties because they are able to intake light and output other light. And so if you've ever heard of a QLED TV, there are these incredibly expensive TVs that use cadmium selenide nanodots or cadmium sulfide nanodots to make incredibly vibrant, rich, and pure colors. And and they're able to do that when you pass a voltage through these nanodots to produce color. But they have really interesting properties, especially with light, because of the Tyndall effect. So, the scattering of light by these colloidal sized particles is known as the Tyndall effect, and one of these is that the atmosphere appears to be a clear uh, gas, but you can find little dust particles when if it's dark enough, and let's say like you sneezed in front of a spotlight, you'd be able to see that. That is the Tyndall effect. And you can also see that illustrated here, where you have a regular solution right here, but as soon as the light from this hits the nanodots or the colloidal species here, you get the scattering of light. It's going to bounce off in all different types of directions, whereas you cannot see it go through here. That's because the particle size is too big to be considered a solution. Um, so fog and smoke are aerosols. You can also think of emulsions as a type of colloid, and one of those, my favorite example, is milk. Milk is an emulsion. It's also soap. Soap is also an emulsion. Or it makes an emulsion when you mix it with water, and that's how it's able to get rid of dirt. And there's also a sol, which consists of solid particles in a liquid, but not as important. Okay. So there's a couple different types of colloids. You have hydrophilic and hydrophobic colloids. Um, hydrophilic, we can break down the word. Hydro meaning water, and philic meaning likes, like it likes it. So like a cinephile um likes movies, a hydrophile would like water. Hydrophobic is like the opposite, it dislikes it. Dislikes. So what it dislikes water, which means that there is no uh interaction between the dispersed phase and the water phase. So another thing that you might, if you are a nurse, you've probably heard of the term coagulation, which is when the dispersed phase of a colloid separates out of this. So this happens to blood a lot. Blood will coagulate and become no longer a mixture, no longer a colloid, but it'll become it will separate and you will get like clots. And um, we can also look at biology in this. Micelle is a biology word, but it also refers to what can happen in a colloid. Um, the cells within a colloid that scatter the light are called micelles. And let's see, is there a picture of one? Not exactly. So I will draw one here. So it looks a lot like what I just drew for the quantum dot. You have a circle. That's because that's what a micelle is. Basically, you have a circle with something inside of it, and then you have another part on the outside that is going to interact with the solvent. So this would be your micelle, and out here would be your solvent. I'll just draw water molecules all around. Could be water, doesn't really matter. And so this part interacts with the solvent, whereas the center does not get to interact. There's too much going on outside of it for it to interact. So one example of this is soap. So this is a chemical that is in soap. It has this really, really long chain. And so the hydrophobic end of the chain, the part that doesn't like water, is going to find all of the grease, all of the food and stuff that does not have any water that's on a plate, for example, and it's going to attract to it. The hydrophilic end is going to be attracted to the water, um, and is going to basically, this is how you can remove the grease from things. So all of these end up surrounding a, let's say that you have like a little chunk of food. You have all of these ends going and surrounding that chunk of food, and they're able to remove it. They're able to basically dissolve it as long as the food is hydrophobic. The hydrophilic stuff would probably just be able to be dissolved in water because that's going to be closer to what water looks like, and um, it is going to be able to be dissolved by that. So that's about where I'm going to end. I'll show you this right here, but this is what the micelle would actually look like. So in the center, you would have some chunk of food. On the outside, you get all of the hydrophilic parts, and you have water molecule as the medium on the outside as well. These are the sodium parts that are going to counterbalance um, the negative charge of the soap molecule. Okay, I think that's about it for today. The rest of this is not super, it's not super useful. So thank you.